We're dealing with dynamics. That is where the net result of the forces is not equal to zero, or the net moments acting on the system are not equal to zero. Because this is different from the case of statics, which I'm sure you've taken as a prerequisite, where here you had that the sum of forces was equal to zero and the sum of moments was equal to zero. In the case of statics, you were looking at the stresses, the strains that would develop, and so on. Well, both of these come under the domain of mechanics. So mechanics is comprised of both dynamics and statics. Now, under dynamics, which is what this entire semester is going to focus on, we can split it further into kinematics and kinetics. So kinematics is what relates to the study of motion, where you're not really caring about the forces and moments. You're only looking at how does the position, the velocity, the acceleration change. So it's like the geometry of motion. And kinetics is the case where you're actually accounting for the forces or moments. With the motion. So motion is related to the position, the velocity, the acceleration. And if we ignore the forces, so here we are ignoring the forces or moments. If we're ignoring that, we're looking at only the geometry of the motion, then that would be kinematics. That is what we're going to study first. So we're looking at kinematics. And to be able to describe the motion, you need to be able to define it in some way mathematically. Right? So for example, let's say that we have some reference. Let's define that as the origin. And let's say along the X, Y, and Z cardinal directions, you're able to take measurements from this point. Let's say that it is purely linear measurements, that is distance measurements, and you have some point, let's say here. You want to be able to define this position with respect to your reference. Intuitively, you want to have some measurements with respect to these cardinal directions. So along this direction, or as a distance from this plane over here, you can have a distance of dx. Similarly, from this plane over here, you would have a distance of dy. And then from this plane over here, you would have some distance of dz, right? So if I were to try and sketch this out, let's say that I mark the height here as dy, and then along this you have dz, and then along this you have dx, right? So this here would be dz, dy, dx. And by these single numbers, so these three numbers, you're able to fully define this position here. Let's say that just the position of this point is sufficient to tell you something about that body. That is, you don't really care about how that body is oriented. And in fact, maybe the body is executing some motion that looks like this, then to define any point along the trajectory, that is, as this is moving in this way, all you need are a series of dx, dy, and dz numbers. So every point, whether it's this one, this one, this one, this one, this one, they're all defined by just their distance from the yz plane, the distance from the xz plane, and distance from the yx plane. Okay, so if this kind of a study is sufficient for you, then this body, where you don't care about how it's oriented and you only care about its position, it can be called a particle. So that is a particle. So it has negligible dimensions. Its position conveys everything we need to localize it. Now the thing is, does it mean that it has to be a point? No, it could be any object. It's just that we don't care about how the object is oriented or how its dimensions are. For example, if you look at the CTA lines, it doesn't really matter if you want to know if the train has reached your station or if it's two stations up before you. You don't really need to know everything about the second position, the second cabin of that train. You just care about where is that entire train, and you just need one particle to define its position. Um, or maybe it's a matter of you driving from Chicago to, let's say, um, Milwaukee. In this case, you don't really care about how your car is oriented, if it is slightly westward or so on. You just need to know where is its position along that distance from the path from Chicago to Milwaukee. Is it at this position? Is it this position? You don't really care if the car is oriented this way or in this way. So all you need is just its position. Okay, or if it's a plane that is going from Chicago to New York, you don't really care about the orientation of the plane, and you only really care about where is it in its trajectory. A point is sufficient to be able to tell you that. Okay, so this here is a particle, and in the very first part of this semester, we'll be looking at particles because it simplifies quite a bit about the analysis. We don't really care about the orientation. And as I kind of described, and just to complete my notes, well, I guess I should say that space is a geometric region that is occupied by the body. That is the region that can be defined by using dx, dy, and dz. Any point in that region is the space. Okay, and the position in space is determined with respect to some known geometric reference. So with respect to, I might sometimes abbreviate to WRT, with respect to some geometric reference system by means of linear and angular measurements. Okay, and so this is just At the moment, we only talk about it as distances, but it's also possible for us to define this point as some angle theta with respect to this and some angle phi with respect to that. It's also possible, right? So for now, we're only going to look at linear measurements, that's just distance measurements. I think 3 classes in, you're going to switch to having angular measurements contribute to the position. Okay, so as a bit of a review, let's now do rectilinear motion. I'm sure you've studied this before, but we need to make sure we're on the same page. So in this, we're restricting ourselves to just one dimension. What does that mean? By one dimension, what I mean is it's only going to be one of these, it's either dx or dy or dz. And just one number tells you everything that you need to know. So it's like the position along a line. So if you have a line here, and you have your origin, or this here is now your reference point. It's generally marked by O for origin. And you define that anything to the right, which is generally the case, is positive. Then a point that is over here, let's say 10 meters away from this, if you just use the number 10, then it means that it is this point here on this line. While if you chose the number as -3, then you would go in the opposite direction, and you have this here as distance being 3 meters, but the direction is negative. Okay, so that's according to the convention. What does this really mean? Anytime that you can represent your space as simply a single straight line, then just by defining one dimension, you're able to have one number to represent any point on that line. For example, the CTA line from, I don't know, 2 different positions. If you were to look at just the position along this, any one number will be able to tell you that your train is at this position. Or if it was a 100-meter dash and this here is a starting point, now 100 meters down, you have your end point, and you can define the position of any person simply by a single number on that line from 0 to 100. Let's actually look at that kind of an example. So I have a photo from the time that Usain Bolt set a record. Let me see if I can bring that in here. Okay. So this here is him having set a record. So a 100-meter dash. In 9.58 seconds. This is Usain Bolt's achievement. So what then is his average speed? With this information, you're able to provide the average speed as simply total distance divided by total time. You can write as V average is equal to, in this case, 100 over 9.58, which should give you 10.44 meters per second. Okay, but in reality, is that true that Usain Bolt had a speed of 10.44 meters per second throughout? Those of you who are in field and track know that in the beginning, of course, your speed is 0, and then you kind of accelerate and you hold a certain speed. And if you can, you keep holding that speed until the very end. But what this means is that this here as an average is a metric that only looks at 2 numbers, that is your total distance and your total time. In reality, the speed might be changing. So if the only information that you had was these two, then all you can say is the average speed. But let's say that using sensors and cameras and so on, it is possible for you to have the true speed at every instant of time. So let's see what that looks like. First, let's plot just what we have as information. So there's a time, in this case at 9.58 seconds, a distance. So distance displacement is usually given by the symbol s. The distance was 100 meters. Presently, all we have is that there is a data point here. This is all we have right now, 100 meters in 9.58 seconds. But if we had more information, and let's say that we were able to plot that information, then maybe that plot looks somewhat like this. Initially, the displacement was changing slowly and then it started increasing. Okay, what does that mean to say that the displacement of the distance was increasing slowly? It means that we're looking at the instantaneous speed, which is essentially looking at a tiny change in time. That would be this here given by dt. And in this tiny instant of time, you're looking at how much is your change in the displacement or the distance covered. So if we were to write that the average speed is given by delta s over delta t, what we've now done is we've made both delta s and delta t go to 0, or essentially just if delta t is going to 0, then what you get is the instantaneous speed. Where v, the instantaneous speed, is a limit of delta t going to 0, delta s over delta t, or equivalently ds dt. That is the slope here. So if this dt were to go down to 0, essentially you're looking at the slope of the tangent at that instant. Okay, now this here might be super straightforward. Bear with me. We are going to do a problem that might challenge your understanding and make sure that you're following me right now. If I were to now sketch out, instead of displacement versus time, if I were to do the instantaneous velocity versus time, what you would then get is something that looks like this, perhaps. Well, in this case, the slope has kind of become somewhat stagnant, right? So at this point, it's somewhat flatlining, which is why I would say this is probably a good representation of your instantaneous speed. Okay. So this v over here is ds dt, which means that going from this to this, all you're doing is the differentiation. And to go from this to this, what are you doing? You're doing integration. Okay, so this here is differentiation of ds dt, and this here is the integration of v dt, gives you what is s. Let's do a quick question before we actually get to the fun stuff. What we're going to do is we're going to consider the case where we have the actual graph of the velocity versus time for Usain Bolt. You'll see that there's a bit of a dip here. We're going to study what happens if Usain Bolt didn't slow down and actually continued to stay at the same speed. And we'll see what could have been the actual fastest time. Okay, so I hope that's interesting. But before that, a quick practice session. So whenever I do a practice session, pause the video and then try to solve it yourself. Just make sure that you're actively learning. That's really important. So I will tell you again to stop, but make sure that you are able to you have a scratch pad or some digital interface in which you can try to solve this yourself. Okay. So here's the question. The speed of a particle is given by v is equal to 10t plus 15t raised to 4 by 3, where v is in meters per second and t is in seconds. If I forget to mention that, always take that as a default. The speed velocity will be in meters per second, time will be in seconds. If at t is equal to 0, that is currently now, it is at the origin, where will it be in 8 seconds? Okay, so pause the video and try this yourself, because I'm sure you've looked at these kind of problems before, and then come back. So how do you approach this? The question provides you with the speed at any instance of time. It's given to you that at the start it is at the origin. So that means essentially we have ds dt is 10t plus 15t to the power 4 by 3. And now we know that to go from velocity to the position, you have to do integration, which provides this here provides you the initial condition. And so here we have the integral 10t plus 15t raised to 4 over 3, integral of this dt. First you have your initial condition as time t is equal to 0, it's at the origin. And at time 8, we're interested in what its position is, that is d. So in this case, you would get s going from 0 to d, which is of interest to us, is equal to, on the right hand side, you will have 10 t square over 2 plus 15. And now this here becomes t raised to 4 over 3 plus 1, that is 7 over 3 divided by 7 over 3. This entire thing is going from 0 to 8. So on the left, you have the distance d is equal to, and here you will have 5 t square going from 0 to 8 plus 15 times 3, that is 45 over 7 times t raised to 7 over 3 going from 0 to 8. And if you were to do this calculation, you will have 1142.8 meters. Essentially, this here will give you 320, and I think this here will give you 822.8. Okay, so in this class, we will be using calculators quite a bit, so familiarize yourself with all the features. What did we actually do in this problem? We have the time and the velocity, and this here is some very high exponential. This is basically what is given by 10t plus 15t to the power 4 by 3. And what it was asking is at time t is equal to 8, what is the distance that is covered, which is essentially the area of the graph here, which is what we just calculated as the integral v dt. It happens to be that this question here says that at the start it is at the origin, which means that just this area would have given you the answer. But if instead they've given you something as a number, say at the t is equal to 0, it was at a position of 100, then what would happen is your definite integral will have again 0 to 8 in the time aspect, but here it would be from 100 to d. And so that'll give you d minus 100 is equal to this, and with that you're essentially doing a definitive integral to account for that initial condition. Okay, so I hope that makes sense. With that, let's do a more interesting problem. In fact, I can show you the true instantaneous speed of a sprinter. It looks something like this. Okay, so this is from some internet source. I believe this is the one of Usain Bolt. It's been a while. As you can see, the instantaneous speed, or the velocity as it's called here. In this class, we make a distinction between velocity and speed in the sense that velocity does involve a direction to be defined, while speed is just a one-dimensional scale or quantity. Okay, so it's like speed is a magnitude of velocity in this class. It varies from context to context, but that's how we're going to call it. So in this case, since it's just the position along that 100-meter dash, what's being shown here is the x-axis is time, and as you can see, the acceleration or the rate of change of velocity or speed is really high in the beginning, and then it kind of increases a little bit here, and then towards the end the speed decreases. Now this here is likely because the sprinter, Usain Bolt in this case, was sufficiently confident that he would win, and so he didn't have to exert as much. But let's say instead that we're interested in what would have been the case if he was able to or determined or just pushed himself to not slow down at the very end. Then the question is, how quickly would he have been able to cover 100 meters? Okay, so essentially in this case, at this time, you know that the area under this graph is 100 meters. What if the graph looked like this? Okay, so I'm going to now sketch out that graph. I'm going to provide you with the numbers. So this here is time t, this here is the instantaneous speed v, and for the first part, we're going to capture it using a function given by v1 is equal to minus 1.31 t squared plus 7.58 t. And for the second part, you're going to keep it as just a straight line that is defined as v2 is equal to 0.375 t plus 10. Now, of course, you could find the intersection of these. I'm just going to provide it to you as this intersection happens at a time of 3 seconds. So for 3 seconds, the rate of change of the velocity is quadratic, and then it becomes linear. Question is, how long to cover 100 meters? Take a moment to pause and think about this question. It's essentially providing you with the instantaneous speed. Here, it's this function. It's for 3 seconds. And then here it is with this function. We're looking for at what instance t will the area under the graph be 100 meters, right? That's what it means. So how do you approach this? You can pause the video and try it yourself. There's a fun one. Okay, so essentially, you have this 100-meter dash starting from 0. In the first part, the speed is changing like this. The area under this curve will provide you with some position here. I'm going to call that as S3. And I'm going to try and signify this by showing that this here, this area here, is equal to this distance here. And for the second part, that is over here, let's say that at some time of t100, so I'm going to define that as t100, you are able to cover that remaining distance. Okay, so that is your approach to this. Um, so S3 will essentially be the integral from 0 to 3 b1 dt, that is minus 1.31 t squared plus 7.58 t dt, which if I were to do it completely will give me minus 1.31 over 3 t cubed going from 0 to 3 plus 7.58 over 2 t squared going from 0 to 3, which gives me a number of 22.32 meters, which means in the first 3 seconds, Usain Bolt covers 22.32 meters. What are we after? We're looking for how long it would take to cover 100 meters, which means now we need to find the area here such that that is equal to 100 minus this. Okay, so area under the line, that is, I'm going to call it as just S from 3 to 100 is equal to 100 minus 22.32. This should be equal to the integral of 0.375 t plus 10 going from 0. No, it's not from 0, right? It's from the time 3 to the time t 100. This much dt, which on the left hand side will give me 77.68 is equal to, on the right hand side you get 0.375 over 2 t square going from 3 to t 100 plus 10 times t 3 to t 100. So if you now put in the numbers of the limits, you will get 0.1875 t 100 squared minus 3 squared plus 10 times t 100 minus 3 is equal to 77.68. And now I'd like to ask you guys to solve for t 100. Again, pause if you haven't solved this entirely yourself. You will get a quadratic equation that is 0.1875 t 100 squared plus 10 t 100 minus 109.37 is equal to 0. And your job is to find t 100. So how would you do that? This is ax squared plus bx plus c form, which means we can use a quadratic formula, minus b plus or minus root over b squared minus 4ac by 2a are your two solutions, which gives me t 100 is equal to minus b plus or minus root over b squared minus 4 times 0.1875 times, in this case, c is minus 109.37, which then gives me, is divided by 2 times 0.1875, which gives me t 100 is either, and if you put this in your calculator, you will get 9.311 seconds or minus 62.645 seconds. Of course, this is a number that satisfies this particular relation, but it is not indicative of the time that would be taken. So 9.31 is the time that Usain Bolt would have reached if he chose not to slow down in this last part, which I'm told is near impossible because there's like the limit of known human endurance. Yeah, but I thought that was an interesting exercise for us to consider. Okay, so all of this was just, we're still limiting ourselves to speed in just, the one dimension. But can we now move on to average acceleration and instantaneous acceleration? We just have to extend our discussion here, where we looked at average speed to be total distance over total time. Average acceleration is total uh, velocity in total time. So if I were to write that down, I have average acceleration, which is A average is equal to delta V, the change in velocity over the time taken. And of course, instantaneous acceleration is just given by A, is the limit of this delta t going to 0, delta V over delta t, which is the differential V over the differential time. Okay, so what does it really mean for us? It now relates your instantaneous velocity with that of acceleration. So let's say that we had some time t, there was acceleration, and let's say that that acceleration is just constant, that is a naught. So what then does this tell us about the velocity? Can you try to sketch it? I'm going to give you a hint. I'm going to define an initial condition as this here is v naught, the initial velocity. So based on this, how would you have a graph for v? Is it something constant? Is it something like this, like that? What is it? It is a constant positive slope, which means that you would have a velocity time or speed time graph that looks like this, where the slope, if time is 1, this, if this here is 1, then this height here would be a naught. And in this case, let's also sketch the displacement. Let's say that time t is equal to 0. The position is given by some s0. Now, the slope of this is given by this, which means that that slope is increasing, which I guess I already sketched that out, but it would be something like this, where the slope is initially something here, and then you can see that the slope keeps increasing, which is what you see here. Okay, and the rate of change of that increase of slope, which is essentially the velocity, is given by this. And the rate of change of that is given by this. So in essence, to go in this direction, you are essentially differentiating. And to go in this direction, you're essentially integrating. Okay, I hope that makes sense. Let's do a problem again, a rather simple one. A particle's acceleration is given by because in meters per second squared. If it's not given, assume that by default. And the time t is in seconds. If its initial position is given by s naught is equal to -1 meters and initial speed is 2 meters per second, find a expression for its position at any time t. So in this case, how would you do this? It's very straightforward. You have just integration to account for. So it's given to you that a, which is dv dt, is equal to 6t plus 4, which gives me v is equal to 6t plus 4 dt, integral 0 to t. If you did this, you would be incorrect. Can you think of why? That's because you didn't account for the initial speed that is given to you. So essentially, you have to do the integral carefully. At time t is equal to 0, it has an initial speed of 2, and say it goes to v. So now you have v minus 2 is equal to, in this case, 6t squared over 2 plus 4t, which gives you v is equal to 2 plus 3t squared plus 4t. And this is nothing but ds dt, right? So I can get ds is equal to 2 plus 3t squared plus 4t dt, integral from 0 to t. This here is, what is the initial position? -1 to the final position, say s. So when you get s plus 1 is equal to, and if you were to do the integration carefully, you will get 2t plus t cubed plus 2t squared. Or the position at any instant of time is given by -1 plus 2t plus t cubed plus 2t squared. This here is your answer. Okay. So this is just a review of integration and so on and so forth. But notice here how the acceleration is not a constant. If I understand correctly, most of you are very familiar with certain relations, which is things like v is equal to u plus at, or v square minus u square is equal to 2as, or s is equal to ut plus half at squared. All of these relations, they require something. Can you think of what that is? For example, can you use this to get these answers? Pause and think. So what you should realize here is that this a has to be a constant, and that's the only way that this will work. So dv dt is equal to a, and in this case where you have dv is equal to a dt, essentially you're integrating from time t is equal to 0 to time t of a dt, wherein dv is going from some initial speed of u to a final speed of v, giving you v minus u is equal to a times t, and that's how you get to this. So that is one important thing. If you were to now start with v is equal to u plus at, so on the right I'm going to write now that v, which is essentially ds dt, is equal to u plus at, then you will have ds that is the displacement. If I were to integrate that, I have s is equal to the integral of u plus at dt going from 0 to t, wherein this here gives you ut plus half at squared. And this again, it requires that u, and I mean u is initial speed, so I guess it's just a number. A has to be a constant, then you get this. Were you able to think about how this comes into the picture? Again, pause and try. This may be unfamiliar to some, but essentially this also requires that acceleration is constant, but what we do now is A is essentially dv over dt, right? That's the acceleration. I can write this using the chain rule as dv ds dt, wherein this guy over here is just ds dt, that is the speed v, right? So I can write that this is v dv over ds, or ads is equal to v dv. Okay, so I just apply chain rule to this using ds. So I have dv ds dt. This here is a speed v at an instant, so there's essentially v dv ds. And now if I were to do the integral, I have this here, ads. In this case, the integral is over the distance, so 0 to s, and v is from initial speed to final speed v. This here will give you v square over 2 going from u to v. This here is a times s, or you will get v squared minus u squared is equal to 2as. Okay, so again, over here, your acceleration had to be constant to be able to write this. Same with this, same with this. So all of these relations, which perhaps you're quite familiar with, only apply when the acceleration is constant, while in this class, we are looking at cases where the acceleration is no longer constant. Okay, so keep that distinction in mind. If this was super easy, then great, this semester is going to continue as an easy course. We're just going to keep going on to these same ideas over and over again. Okay, so with that, let's look at now a case where you have acceleration that is defined based on the velocity. So this is commonly a case when you have some kind of a fluid behavior, so things like air resistance and drag and so on. Okay, so in this case, you have a space shuttle of mass m lands with an initial velocity of v naught and then deploys a parachute. That causes a deceleration given by a is equal to minus k v squared. Okay, so deceleration is when your acceleration has a negative value. If it's given as a is equal to minus k v squared, this in itself means that it is a deceleration. The question is, what is the distance d traversed when the velocity becomes vf? Okay, so think about how you're going to solve this problem. Pause the video and then let's return. Okay, so in this case you have that a is equal to minus kv square. So it is not a constant and is changing based on the velocity. So this minus kv square is the acceleration, and we have that a ds is equal to v dv. Right, so if we were to apply this, you get minus kv squared ds is equal to v dv, or minus k ds is equal to 1 over v dv. Now you do the integral, it goes from an initial speed to final speed over some distance which is of interest to us. Actually, this distance is given as distance d. So in this case, minus k times d is equal to, now what is the integral of 1 over v dv? You should know this. This is ln of v going from v0, v0 to vf, which will give you ln of vf minus v0. Ln of vf minus ln of v0, and using the logarithmic properties, you will get this is ln of vf over v0 is minus kd, giving you finally d is equal to minus 1 over k ln of vf over v0. So the distance covered to go from a speed of v0 to vf is given by this. Okay. With that, we'll conclude this tiny module as a bit of a review, and then we'll move on to the review of vector differentiation and so on.